And we can also start to look at the extent of recycled material if we're looking at isotopic traces such as sulphur in the mantle. And in order to do this and to look at like eruption style and planetary atmospheres, we need an accurate and quantitative model of degassing. And today I'm just going to talk about modeling the chemical changes that occur in the melt and the vapor. Obviously, there are lots of important physical effects that occur as well, but today will just be about the chemistry. So the major volcanic volatiles are obviously water and CO2, but sulfur is typically the third most abundant volatile element in magmas. And it's a really important element to model in volcanic degassing because it has a wide range of valence states at magmatic conditions. So it can be present in S2- all the way up to S6+. And this means it can be present in lots of different phases in our magmatic system. So it can be dissolved in silicate melts, it can be exolved in a gas phase, it can form its own immiscible liquids or even solid phases, and also be dissolved in aqueous fluids. And on top of that, within each of these phases, it can be present in lots of different species. So in a silicate melt, for instance, we can have dissolved sulfide and sulfate. And in the gas phase, we can have things like hydrogen sulfide and sulfur dioxide. So if we want to model the behavior of sulfur accurately during degassing, we need to be able to model sulfur in all its different phases and species. And because of this range of valence states that sulfur has, it's really important if we want to understand how oxygen fugacity changes during degassing. So oxygen fugacity is related to the chemical potential of oxygen in the system. And it's basically to do with how much oxygen is available total, but also how that oxygen is partitioned between the different phases in the magma. And the reason we want to know how oxygen fugacity changes is because it has quite important effects on the chemical and the physical properties of the melt. So there are a wide range of approaches for looking at sulfur during degassing, from purely empirical models to fully thermodynamic models. At the empirical end, we have codes like SOLEX, which is widely available, or parameterizations of the solubility of sulfur from experimental studies. And then we also have more thermodynamically inspired approaches, such as that's available in decompress. And here I've just shown examples of what the relationships they use between the melt and the gas are for sulfur. And with these empirical approaches, the functional form chosen to fit the data is somewhat arbitrary or kind of related to the thermodynamics, but it makes it very difficult to extrapolate beyond the experiments very much. On the other hand, we could use a fully thermodynamic approach. And in this case, we don't need to guess the functional form that relates the sulfur content in the melt to something about the gas phase, because we can infer it from the reactions that we're going to use to explain the degassing process. And this means that we get quite simple relationships between the melt and the gas. To use this approach, you need a lot of thermochemical data, but we can get that from experiments. And currently this approach isn't used in any of the widely available codes that you can just download, but this is the approach I'm going to use here. So a quick outline of the talk, I'm just going to describe the model first of all, and then depending on the time, I've got 3 applications to show, looking at how sulfur, oxygen fugacity and water affect calculations of the pressure of vapor saturation, degassing trends, and also how we can estimate the oxygen fugacity from the total dissolved sulfur content. And all of this is kind of aimed at being able to interpret melt inclusion data predominantly. So this is a picture of a crystal containing a melt inclusion, this little brown blob here. And basically melt inclusions are little pockets of melt trapped inside crystals as they grow from the magma chamber. And once they're fully enclosed by the crystal, we hope they kind of maintain the composition they're trapping. Because they're separated from the rest of the magma, as they ascend, they don't undergo degassing. So we can get volatile contents that are much higher, and they kind of track the degassing process. Obviously, there's a lot of caveats for using melt inclusion data, but they do give us some sort of record of the degassing process. And to interpret that data, we need better models to do that. So first of all, I'll describe the model. So as I said, it's going to be a thermodynamic-based model. And we're going to consider sulfur, carbon, hydrogen, and oxygen as the elements. And the first thing to do is to decide what species we're going to be looking at in the melt and the gas. So in the gas phase, we're going to have 10 species. So they're going to be sulfur, hydrogen, and carbon monoxide for our reduced species, and then sulfur dioxide, water, and carbon dioxide for the more oxidized species, and oxygen. And then we've got 3 cross species, so hydrogen sulfide, carbonyl sulfide, and methane. So I should just say that in a gas that contains sulfur, carbon, hydrogen, oxygen, there are other species that could be present. So we could have things like CS2 or SO3, but those will typically be in concentrations than these 10 that I've specified here at the conditions that we're going to be looking at. We could also include other elements, so things like fluorine and chlorine, but really, I just want to concentrate on adding sulfur to this system, and also the constraints on the solubility of these other volatile elements is less well constrained. And then we need to look at what's going to be in our melt. So I'm going to consider water dissolved as hydroxyl ions. We also can have oxidized hydrogen being dissolved as molecular water, but this approximation of using hydroxyl ions is appropriate up to quite high water contents, and it does simplify the problem quite a bit, so it's useful to use this approximation for now, but adding in molecular water wouldn't be that hard. I'm going to concentrate on looking at basaltic melts. So the oxidized carbon species that I'm going to include is carbonates, CO3 2-. In more silica-rich melts, you would get molecular carbon dioxide. Again, this could be added, but for now, we're just going to concentrate on basaltic melts. And then I'm going to consider 3 reduced species of hydrogen that are hydrogen and carbon bearing. So I'm going to have molecular hydrogen, molecular methane, and molecular carbon monoxide. The data available to model their solubility is pretty limited at the moment, but there is data available, so it is useful to see how they influence the system. For the sulfur, we're going to have oxidized sulfur as sulfate and reduced sulfur as sulfide. And then because we want to look at changes in oxygen fugacity, I'm also going to include iron in the melt. So we've got iron 3+ and iron 2+. So once we've got the species that we're going to model, we need to have reactions that are relating the gas and the melt phase. And I'm not going to go through all of them, but I'll just give an example of one of them to kind of explain the concept, and then show you how we're modeling sulfur, as that's the thing that's a little bit different. So if we wanted to consider how hydrogen dissolves, we could say that hydrogen in the gas dissolves as molecular hydrogen in the melt. And we can write an equilibrium constant for this reaction, which is denoted here by K, and K is a function of pressure and temperature. And K is equal to the activity of hydrogen in the melt divided by the fugacity of hydrogen in the gas phase. We can expand out these activity and fugacity terms, and we can say that the activity of hydrogen in the melt is the activity coefficient, so gamma m, times the mole fraction of hydrogen in the melt. And this activity coefficient is to describe the non-ideality in the melt, but we typically assume that the melt species are behaving ideally, and in this case, this gamma term is just 1. For the fugacity, it will be the fugacity coefficient, so gamma g, times the partial pressure of hydrogen in the gas. And this partial pressure of hydrogen is important for when we want to calculate pressures of vapor saturation. We can further expand this partial pressure term to be the mole fraction of that species in the gas times the pressure of the system. And in this way, we now have an equation that relates a compositional component in the gas to its concentration in the melt. And we can write similar equations for all the different species, and this is typically how we model water and carbon dioxide solubility in melts. For sulfur, we're going to use the ideas of sulfide and sulfate capacity, which are pretty old. So they originally come from Finchman and Richardson in 1954, but they haven't been particularly used in widely available codes for degassing so far. And basically what it says is that if we have reduced sulfur, so S2-, it dissolves in the melt by replacing oxide in the melt. So we could write an equation such as this shown here, thinking about iron species, where sulfur in the gas reacts with iron oxide dissolved in the melt to produce oxygen and iron sulfide dissolved in the melt. And we could write an equilibrium constant for this reaction. that says that K, which as I said depends on pressure and temperature, is the ratio of the activity of iron sulfide to the activity of iron oxide times the square root of oxygen fugacity divided by sulfur fugacity. We could write similar equations for all the different silicate melt constituents. So I could write one for like calcium and sodium. And then if I wanted to know the total amount of sulfur dissolved in the melt as sulfide, I would just add up all the contributions from the different dissolved sulfide species. And that would be described by this equation. So here we say that the total sulfur content of the melt dissolved as sulfide, so S2 minus, is the sulfide capacity times the square root of the sulfur fugacity divided by the oxygen fugacity. And this sulfide capacity is basically the equilibrium constant for each of those constituent parts times the amount of that oxide in the silicate melt. For sulfate, we can write a similar equation, so that's shown here. And you'll see that in this case, the sulfate content dissolved in the melt is equal to the sulfate capacity times the square root of oxygen fugacity cubed times sulfur fugacity. So because we have a different stoichiometry to this equation to create sulfate in the melt, we get quite a different relationship to the gas phase. And that's going to give us really interesting behavior when we change the oxygen fugacity of the system. So once we have these two equations, we have a way to relate what's in the melt to what's in the gas. And the nice thing is that once we have the thermochemical data to describe the sulfate and the sulfide capacity, we have a simple way to model the behavior of sulfur during degassing. And we haven't had to use an arbitrary form of the relationship, unlike more empirical approaches. But how well do we know these thermochemical parameters, the sulfide and the sulfate capacity? Well, the sulfide capacity is pretty well calibrated for changes in melt composition and temperature. So the most recent compilation is by O'Neill last year, and this plot here shows the calculated sulfide capacity against the observed sulfide capacity from experiments, and their model gives a pretty good fit to the data, and it's a lot of experiments that have gone into this, which is great. On the other hand, the sulfide capacity is poorly calibrated for the effects of pressure and water. And this is because most of the experiments used are done at 1 atmosphere, where you get really good control of oxygen and sulfur fugacity, which you need to calculate the sulfide capacity. So in the future, it'd be great to have better calibrations to include the effect of pressure and water. The sulfate capacity is much more poorly constrained, so we don't really know the effects of pressure, temperature, or melt composition on it. And that's because there hasn't been a kind of experimental effort to constrain this parameter. This plot that I'm showing here is data that I've got from the literature, from experiments in squares or studies on melt inclusions in diamonds, where I'm able to calculate a sulfate capacity from the available data. And I can explain how I do that, but what we can see is that we get a relationship with temperature. So we get a decrease in the sulfate capacity as we increase the temperature. But at a single temperature, we get quite a wide range of sulfate capacities. And this implies there's some sort of compositional control on it as well. This black line here is from Nash et al. In 2019 from their relationship between the sulfur and the iron oxidation state, which we can use to calculate a temperature dependence of sulfate capacity. And we see that there's a bit of a deviation between what the data is suggesting and what this fit would suggest. So the results I'm going to show you are obviously do depend on this sulfate capacity. So the magnitude and maybe the exact oxygen fugacities where things are happening will vary depending on the choice of this parameter. But the broad trends that I'm going to show are kind of independent of that. So I'm just going to use a value from this Mauna Kea data here at about 1200 for the calculations that I'm showing. So just a quick summary of the model. It does equilibrium isothermal decompression, so I'm not going to consider any changes in the melt composition apart from its volatile content during degassing. On top of those reactions I showed you between the melt and the gas, we also have reactions going on in the gas phase, so homogeneous equilibria, in order to produce species like carbonyl sulfide, which don't dissolve in the melt. We then have chemical and isotopic mass balance, and then that allows us to calculate the distribution of all these species between the gas and the melt at a given pressure and temperature. The nice thing about it is it's thermodynamically consistent. We can track changes in sulfur and iron speciation together, and it's really easy to calculate isotopic changes using this model, which aren't done in currently available codes. So first of all, I'd like to talk about how we can use this model to understand the pressure of vapor saturation. So we often use the dissolved volatile content of glasses as a barometer to infer pressure. So for instance, we often use water and CO2 concentrations in melt inclusions to understand magmatic plumbing systems and work out where magma is stored prior to eruption. Or we can use water and carbon dioxide concentrations in matrix glasses from subaqueous eruptions to infer the depth of eruption. And the way this works is you take a dissolved volatile content like water, you use one of those solubility relationships I showed earlier to calculate the fugacity of water in the gas phase. And then using the fugacity coefficient, we can calculate a partial pressure. And if we do this for the different volatiles in our glass, we can sum up all those partial pressure contributions and use that to calculate the total pressure of the system. And this will give us the pressure of vapor saturation. This obviously presumes that there is a vapor present, and if there wasn't a vapor present, then this will just be a minimum estimate for the pressure that that glass is recording. There are lots of available codes out there to calculate the pressure of vapor saturation, such as volatile calc, magmasat, and a new one, VCal. And these models tend to assume that hydrogen in the melt is dissolved as hydroxyl ions or molecular water, and that if you're looking at a basaltic system like we are, that the carbon is dissolved as carbonate. They also assume that the gas is just water and CO2. So what I want to look at is how including reduced carbon and hydrogen species, both in the melt and in the gas phase, changes the calculated pressure of vapor saturation, and also how including sulfur also affects it. And to do this, I'm just going to use a toy model where I'm going to take a basaltic composition at 1200 degrees Celsius, and we're going to keep the total amount of hydrogen and carbon in the melt constant, and we're just going to vary the oxygen fugacity of the system. And then later we'll add sulfur to see what that does as well. So on this plot on the right, I've got the oxygen fugacity on the x-axis, which is going to be in units of delta FMQ. So this is relative to the fayalite magnetite quartz buffer, and more positive values are more oxidized conditions, and more negative values are more reduced conditions. And I've just put here at the top some kind of reservoirs to kind of anchor what these values mean. So Morb is typically at about 0. Arcs are at about maybe +1 to +3, and somewhere like Mars would be down at -3. On the y-axis, I'm plotting the calculated pressure of vapor saturation. So this is PV-sat, and this is going to increase downwards. And I've just shown what the equivalent depth roughly would be to help anchor those values as well. So firstly, I'm just going to calculate the pressure of vapor saturation for a melt that only contains hydroxyl ions and carbonate ions. So there's no sulfur in the system, but the gas is allowed to contain all the different carbon, hydrogen, oxygen species. And if we do this calculation at high oxygen fugacities, we see that there is no effect of oxygen fugacity on the calculated pressure. And that's because the gas is dominated by carbon dioxide and water. So this plot on the bottom is the log of the fugacity of the different species in the gas phase. So just a reminder, the fugacity is equal to the fugacity coefficient times the partial pressure. And we can see that in these oxidized conditions, our gases just basically carbon dioxide and water, and these reduced species are a tiny amount because this is a log scale. So these are truly very small concentrations. On the other hand, as we go down to more reducing conditions, we see that the calculated pressure of vapor saturation increases rapidly and is really quite different from its value at high FO2s. And that's because the gas phase is becoming dominated by these reduced species. So we're dominated by carbon monoxide, and we're getting a lot of hydrogen and methane. And because their fugacities are increasing, the partial pressures are increasing too, and this leads to greater pressures of vapor saturation. But we know that at more reducing conditions, the dissolved volatiles aren't just hydroxyl and carbonate, they're also hydrogen, methane, and carbon monoxide. So we can include those in our calculations, and that's what's shown in this orange line here. And now we see that the calculated pressure of saturation still increases as we lower the oxygen fugacity, but to a much it's a lot less than the effect of when we didn't include these reduced species. And that's because in the gas phase, what happens is, the hydroxyl and the carbonate will be converting to these molecular reduced species, and that reduces the fugacity of the water and the carbon dioxide. And these reduced species, CO and hydrogen, don't get up to as large a values, so we don't see as large an increase anymore. So what happens if we add sulfur? So here I've just rescaled this to get rid of the curve that didn't have any reduced species in the melt, just to show the effect a little bit better. And if we add sulfur, we see quite interesting behavior with oxygen fugacity. So at low FO2s, we don't see an effect of sulfur, but in more oxidized conditions, we get this maximum in the pressure of vapor saturation. And this maximum is coinciding with a change in the oxidation state of sulfur. So this dark gray curve I'm showing here is the S6 plus to S total ratio calculated at the pressure of vapor saturation. And this sigmoid is occurring because sulfide in the melt reacts with oxygen in the gas to form sulfate. And this has been shown in experimental studies such as Hughes et al. In, I think, 2010. And it's related to this equation we can write here, where the S6 plus to S2 minus ratio is the sulfate to sulfide capacity, where the sulfite to sulfide capacity is basically the equilibrium constant of this reaction, times the oxygen fugacity squared. And that's why we get this sigmoid shape, because it's FO2 squared. And this change in the sulfur speciation in the melt has a big effect on the composition of the gas phase. So here I'm just showing the fugacities of the different sulfur-bearing species only, and we can see that they all show a kind of turning point where we're getting the maximum pressure of vapor saturation. And we can look at this in three parts to understand what's happening. Firstly, at low oxygen fugacities, our melt is dominated by S2 minus. And this means the reaction that's controlling the solubility of sulfur is this one here, which I'm showing. And this means that the sulfur fugacity is directly proportional to the oxygen fugacity. And that's because this S2 minus concentration is constant because all of our sulfur is S2 minus and the sulfur content is constant. To calculate what's happening to SO2, we can look at this homogeneous gas equilibria. So we can produce sulfur dioxide by reacting sulfur with oxygen. And in this case, we get the following equation here. And if we substitute in this relationship that we derived from knowing that all our sulfur is sulfide, we find that the fugacity of sulfur dioxide is proportional to the fugacity of oxygen to the power of 1/2. So both these species are increasing as we increase the oxygen fugacity. When we go to more oxidized conditions, all our sulfur is now S6 plus, and we look at the other dissolution mechanism here. And instead of being proportional to oxygen fugacity, our sulfur fugacity is now proportional to the oxygen fugacity to the -3. And this is reflected by this really steep decrease in the sulfur fugacity as we increase oxygen fugacity. And again, we can look at this reaction for sulfur dioxide, and we find that the fugacity of sulfur dioxide is proportional to the oxygen fugacity to the -1/2. So it also decreases, but much less steeply. And in the middle, we're getting a trade-off as we're changing the speciation of sulfur. And when we're sulfide dominated, we're going to see that the sulfur fugacity the sulfur dioxide fugacity increases with FO2. And then when we're sulfate dominated, we're going to see that the sulfur dioxide fugacity decreases, and that's what's giving us our maximum. And the reason that it's actually having a measurable effect on the pressure of vapor saturation is because this value of the sulfur fugacity is kind of similar in magnitude to the fugacity of carbon dioxide and water, which are really controlling the calculated pressure of vapor saturation at this fugacity. And we can see how this applies to natural data and what effect it might have. So here I've taken some data from a paper by Gennaro et al. Last year, where they looked at melt inclusions from a variety of eruptions at Etna. And they measured the volatile content and the ion speciation in them, which allows us to use this pressure of vapor saturation calculation. So here I'm just showing their CO2 and water data. And here what I've done is just showing you the spread in the ion oxidation state they have. And I've calculated the pressure of vapor saturation, but assuming there is no sulfur in the system. And that's in these blue diamonds. We can then calculate what the pressure of vapor saturation would be if we included sulfur. And that's in these open squares. And we see that in all cases, we increase the calculated pressure of vapor saturation. And just to highlight how large the magnitude is of this effect, here I'm just plotting the difference between the diamonds and the squares. And we can see that when we're at high sulfur contents of like 3000 ppm, we're getting maybe 700 bars extra pressure from these sulfur bearing species, which could be changing your depth by quite a lot. So next I'd like to talk about how sulfur, oxygen and fugacity and water affect degassing trends, including their effect on isotopes. And this is really motivated by the fact we have a lot better and more comprehensive studies of melt inclusions, which means we have a lot of information about the degassing process, including like concentrations, the speciation of redox sensitive elements, and also isotopes. And what we need is a model to be able to interpret that. And in particular, I've just highlighted some recent studies that have created data that really speaks to this. Would be, we often see that sulfur is degassing deep in hydrous systems. And by that, I mean in places like Kilauea, we think that sulfur degasses really shallow and it's a relatively dry system. Whereas in arcs, we see that water is degassing really deep. Sulfur is degassing really deep. And what is the influence of water, as that's a big difference in those two systems at controlling the behavior of sulfur. Also, we want to know how sulfur affects the oxygen fugacity during degassing. And finally, now that we can measure the sulfur isotope ratio of melt inclusions, how can we predict how the sulfur isotope ratio changes during degassing? So to explore this, I'm just going to use a toy model again. So here we're going to have a basaltic melt at 1200 degrees C, and it's going to have constant carbon content and sulfur content. And we're just going to change the water content in the melt from quite dry for about half a weight % water in red to very hydrous at 5 weight % water in blue. And that's to kind of reflect maybe MORBs all the way up to arc systems. The other thing we're going to change is the oxygen fugacity that the system starts at, and solid curves will be a delta FMQ of 0, and dashed curves will be a delta FMQ of plus 1.5. And then we're going to allow the melt to saturate in a vapor phase, and we'll start the calculation from the pressure of vapor saturation and degas it to 1 bar under closed system conditions. So first of all, we can look at what the sulfurs during degassing. So this plot here shows the sulfur content on the x-axis against the pressure on the y-axis, and pressure is increasing down. So this orange arrow is showing the direction of degassing, so from the bottom of the plot to the top. And what we can see is that there's a wide range in the behavior of sulfur as we change the water content and the oxygen fugacity. And we see that in hydrous conditions, we're getting deep degassing of sulfur. And this is because of changes going on in the gas phase, because I should say that in these calculations, there's no effect of water on the solubility directly of either the sulfide or the sulfate phase in the melt. So this is all to do with changes in the gas. So here I'm plotting the gas composition. So this is the sulfur dioxide composition on the top and the hydrogen sulfide composition on the bottom. And what we can see, for instance, is that under reducing conditions, we're getting a lot of hydrogen sulfide produced at depth. And this is driven by this reaction here. So sulfur reacts with water in the gas to form hydrogen sulfide and oxygen. And when you've got a lot of water in the system, this drives the reaction to the right to produce H2S. And therefore, we need to be degassing sulfur from the melt to provide the sulfur in the gas. We can also look at how the oxygen fugacity is changing during this degassing trend. So here I'm plotting the oxygen fugacity of the melt against pressure again. And we can see that when we start off reduced, we get very different behavior to when we start off oxidized. And I should just say that in the background to the effects of sulfur, when we degas carbonate and hydroxyl ions from the melt, we're always going to get oxidation of the melt. So the melt FO2 will always increase. And that's because when carbonate and hydroxyl ions degas, they form carbon dioxide and water in the melt. And these two species disproportionate to form carbon monoxide and hydrogen. And this is accompanied by the release of oxygen. So this is causing oxidation of the system. The magnitude of this effect depends on how much of the species is exsolving, but also the initial oxidation state of the system. But the background will always be that the melt will oxidize when these two species degas. So on top of that, we see an effect of sulfur. So we can understand this by the different reactions that are occurring. So if we start by looking at the reduced case here, and we look deep in the system, we see that there's not really any change in the oxygen fugacity during degassing. And that's because under these reducing conditions, sulfur is dissolved as sulfide, so S2-, and it's degassing to hydrogen sulfide, which is also S2-. So there's no change in the sulfur oxidation state, and therefore there'll be no change in the melt oxidation state. If we go to shallower in the system, in the reduced case, we now see that the melt reduces during degassing. And this is because we've still got sulfide in the melt, so S2-, but our gas is now dominated by sulfur dioxide. So in this case, sulfur has an oxidation state of +4. So we've now oxidized our sulfur, so the melt has to reduce to compensate for this. And then if we look in the oxidized case, we see that at low pressures, we get oxidation of the melt. And this is because now our melt is dominated by sulfate, so S6+, and our gas is still dominated by sulfur dioxide, so S4+. So we've had a reduction in the sulfur and the melt is oxidizing to compensate. And we can see how this affects the isotopes too. So here I've just plotted the total sulfur content of the melt on the x-axis, and then the isotopic composition of the melt on the y-axis. And I'm using here delta 34S notation, and it just means that if we've got more positive values, the melt is heavier, so contains more 34S. And if we've got more negative values, the melt is lighter and contains more 32S. And I should say that we can see that depending on the initial oxidation state, we're getting very different behavior of the sulfur isotopes. And this can be explained using the same reactions. So in the reduced case, we have sulfide always in the melt, and it either degasses to sulfur dioxide or hydrogen sulfide. But in both cases, the melt prefers to have the lighter isotope of sulfur, and therefore as degassing proceeds, our melt gets lighter and lighter. On the other hand, when we're in the oxidized case, our melt is dominated by sulfate in the melt, and this prefers to have the heavier isotope compared to the gas. So we end up, as degassing proceeds, to getting heavier and heavier melt. And then we can apply this to natural data, for instance. So these are data from Brown et al. In 2017, where they measured the volatile content of matrix glasses from Mauna Kea in Hawaii. And here I'm just showing the sulfur versus water content, the iron 2+3+ ratio over the water content, and the sulfur oxidation state against the water content. And using this model, we can match this data pretty well. And it suggests that the reason with this we're seeing reduction during degassing is because we're having equilibrium degassing under closed system conditions. I'll just skip this one to leave time for questions. But I just want to put up these conclusions and just quickly highlight two initiatives that might be of interest to this community. The first one is called Geocontext, which is a project producing supplementary curriculum aimed at providing a social and political context for geoscience. And it's a series of teaching modules that are freely available online at this website. And we're looking for contributions from the community. So if anyone has an idea of some material they'd like to put together, we'd love to hear from you. And then a lot of people will be aware of Volcanica, but just to highlight that Volcanica is an open access, a Diamond open access journal for volcanology, which is free to read and free to submit to. So if you have any studies that you're looking to publish, do consider this journal. And I'll stop there and take any questions. Thank you for listening.
Thank you, Ery. That was really great. We definitely have time for questions and discussion. Please feel free to raise your hand or put a question in the chat room if you'd like. We're a small enough group that you can unmute yourself once I've called on you with your raised hand. And Ery, while people are kind of organizing their thoughts, I guess I had one question, and I was kind of thinking in the back of my mind, how does this, how will this change our, what are the implications, I should say, of this towards non-equilibrium degassing scenarios? And I've wondered if you thought about this much, like in a sort of conduit setting or something like that.
So I'm not sure how it would affect non-equilibrium degassing, but I think it's important that we understand the equilibrium process before we try and move towards understanding the non-equilibrium process. But I am really interested in how the kinetics are important. So Xenia Boys, who's probably on the call, she's a PhD student of Ed's and is looking at how we can model kinetic effects during degassing. And it'd be great to couple this kind of model with a kinetic model, because this allows you to give a boundary condition to those non-equilibrium models to look at things like transfer into bubbles and things.
Yeah, absolutely. Thank you. Other questions? Okay. Okay, we've got a question in the chat here. Penny asks, great talk, Ery. My microphone has been broken, so I'll type the question. Okay. I'm interested in the effect of melt composition on your model. Do you only include iron oxide, Fe2O3 in terms, and FeO and Fe2O3 in terms of melt terms, or also calcium, magnesium, and Al2O3, which has been shown to be important? Say Shishkina for CO32.
Yeah, so firstly, all the calculations that I showed were done for a single melt composition. So we don't have any change in the melt composition during the calculation. So the degassing process is assuming there's no crystallization. In terms of how the melt composition affects the different solubility constants, currently, for instance, for water doesn't have a huge effect, so I haven't really been looking at that. The carbon dioxide solubility is a big problem, and we really need a better model to understand the effects of composition on the CO2 solubility, because that'll obviously affect at what pressure all of these calculations start. That is definitely a really important part. For the sulphur, the melt composition is taken into account for the sulfide capacity. The O'Neill model has a pretty good parameterization for that. As I said, for the sulfate capacity, there's currently no inclusion of a compositional term, it's just temperature. And in terms of iron 2+ and iron 3+, I don't take the change in the speciation of sulfur of iron whilst we're degassing to affect the solubility constants at the moment. And that's mainly because there's not a lot of data available, but it would be possible to include those effects if the data was available.
Thanks. And if anyone has follow-up, please feel free to add it here. Terry Plank has a question about deep degassing of sulfur. And Terry, if you want to just unmute yourself, if that's possible, you can just do that.
Hey everybody, hey Ery, that was such a super lucid talk, thank you, and super important work. It went by a little quickly, but one of our challenges is now that we find out that sulfur is degassing at higher and higher pressure, because melt inclusions have more and more CO2 than we thought, and so the pressures have gone up. It seems a challenge to have that happen, maybe in your model. So it seemed that having sulfur degas at depth required some strange combination of it being wet and low FO2, is that? And so, but that's not going to explain like ARCs where, you show Dan Rasmussen's beautiful data showing that it's deep degassing of sulfur. Thanks.
Yeah, so yes, I agree. So We still see, so yeah, this was the plot where I showed that for the reduced case, we definitely see really deep degassing of sulfur from this hydrogen sulfide coming out at depth. But we still see deep degassing of sulfur even in the oxidized case here. So it will be coming out of solution much greater depths than in the dry case. So I think the fact there's water present is still influencing it, and that's, it doesn't show up in these, yeah, but I think the model still predicts deep degassing of sulfur here. It's just not as pronounced as in the reduced case. And I think this, I should say that these results here are really dependent on the sulfate capacity that's chosen. So I'll just, for example,
and the pressure terms on the sulfide capacity too, which are tricky, right?
Yes. Absolutely. So currently there's no pressure effect on the sulfate capacity or the sulfide capacity. But just for an example here, this is the sulfur content of the melt against pressure. And we can see that here I've just changed the value of that sulfate capacity. And I think this was done, so this was starting at relatively reduced at delta FMQ of 0. And we can change the behavior of sulfur from degassing really deep to degassing really shallow by changing this parameter. So I think that when we have a better handle on the sulfate capacity, it'll be the interpretations for natural data will be much more robust.
Super, thanks, Ery.
Thanks.
Are there questions out there? Ery, you've certainly shown a few data sets here. Is this something you're going back and kind of actively sort of thinking about correcting perhaps some inferences for pressure? I mean, this is a very, obviously needs something about the oxidation state, but is this something that you would advocate going back and trying to make these corrections where applicable?
Yeah, it'd be great to look through data sets that, if they've got high sulfur, then this might be important. I would say that I think probably a more important thing for when calculating the pressure of vapor saturation is to check what CO2 model people are using. So volatile calc is calibrated for a very specific composition. And if you're in more alkalic systems, it's still going to be the CO2 solubility term that really defines what the pressure is going to be calculated at. So I think that's probably more important. And something like VCal, which I mentioned at the beginning, allows you to explore the effect of that CO2 term, which is probably more important at the moment than the sulfur.
Thanks, that's great. Roy has a question. Roy, you can just unmute yourself.
Hi, Dr. Hughes. Thank you very much. That was a very enlightening talk. I thought it was pretty interesting how the species change regarding oxygen fugacity. I thought that was really interesting. So I guess I'm curious, if you have, let's say, pyrite, for example, what sort of scenario, because you would need, I assume you would need low oxygen fugacity conditions. What sort of scenario would you envision for, say, the formation of pyrite and quartz veins, like along the margin of granites, for example, in these upper crustal conditions?
Well, I have no idea. So the models that I've been looking at, we just consider maybe sulfide precipitation, so like as S2 minus. So I haven't really looked at how pyrite would form. So sorry, I'm not really sure what that would imply. And unfortunately, for instance, the sulfide capacity is only really calibrated for like basaltic compositions. So more felsic systems where you might get quartz veins would be quite different. So sorry that I can't be more helpful on that.
Okay, no worries. All right, thank you.
Any last questions? All right. Well, Ery, thank you so much. This was an excellent talk. I think we're all excited to apply your model to our various systems. Everyone, please join us again next week, and please feel free. I think what we'll end up doing here, if Ery has time now, is just kind of adjourn. But if you want to stick around and have a little bit of one-on-one discussion, there's always sort of that sort of effect where it's sort of like seeing people at the podium after the talk, I guess. And there are always a few questions that way too. So please stick around if you have a little bit smaller discussion item. But otherwise, join us again next week. Good seeing everybody.